The Voyager probes left the launch pad in 1977, but their engines have been quiet for decades. Having acquired enough energy to escape the sun's gravity well, they are now coasting through the frictionless vacuum of interstellar space. Dictated entirely by classical Newtonian physics, they will continue moving in a straight line forever, unless acted upon by an outside force. But coasting through the void is not the same thing as exploring it. To be an active explorer, a probe has to observe its surrounding environment, record those observations, and successfully beam that data back to scientists on Earth. And that is where the Voyager missions are hitting a wall. After nearly half a century in the deep cold of space, these incredibly resilient machines are actively dying. They are losing the ability to observe and the ability to speak. This timeline illustrates a harsh reality of deep space missions. Every probe actually has two separate lifespans. The first is its operational lifespan, a tiny, bright window where it has the power and signal strength to phone home. The second is its artifactual lifespan, a long, dark existence where it drifts as a dead, silent piece of metal for almost eternity. When you look at modern deep space engineering, you are looking at an ongoing war against physics. Every command sent by mission control is a desperate attempt to stretch out that first, fragile operational lifespan for just a few more months. The first major hurdle in extending that lifespan is generating power. Once a spacecraft travels past Jupiter, the sunlight becomes incredibly dim. Solar panels are entirely useless out here, which forces deep space probes to carry their own internal power plants. Voyager's power plant is a Radioisotope Thermoelectric Generator, or RTG. Instead of solar or chemical power, RTGs harness the natural breakdown of radioactive material, specifically pellets of plutonium-238. This intense red glow is the manifestation of raw thermal energy, generated entirely by the spontaneous radioactive decay of the fuel pellets. Thermocouples inside the RTG convert that temperature difference between the glowing plutonium and the freezing vacuum of space into electricity. But you cannot cheat the math of radioactive decay. As this chart shows, Voyager's power output is steadily diminishing. Plutonium-238 has a half-life of 87.7 years, dropping thermal output predictably. This costs the spacecraft about 4 watts of power every year. To survive on this steadily shrinking budget, Mission Control has to perform relentless triage. Engineers have been systematically, permanently shutting down scientific instruments, cameras, and even internal heaters. They are trading away observational capabilities just to keep the spacecraft's core processor from freezing. Engineers are already developing next-generation power solutions to avoid this exact bottleneck in the future. Technologies like nanotritium batteries harness the decay of rare isotopes. Instead of generating high heat, these batteries provide a highly predictable, lower wattage power supply designed to survive cosmic radiation and near absolute zero temperatures for decades. Success in the deep freeze of the outer solar system relies on our ability to precisely harness and rigorously budget nuclear decay. Having enough power to turn on an instrument is only half the battle. Generating that data is useless if the spacecraft cannot push the information across a 15 billion-mile gap back to Earth. This geometric visualization shows exactly what happens when spacecraft hit the inverse square law. When Voyager transmits a 20-watt signal, that radio wave expands outward spherically. By the time it crosses the solar system, the energy is so severely diluted that it hits Earth at roughly 7.22 times 10 to the negative 19th watts, a microscopic fraction of a whisper. Catching a signal that weak requires terrestrial brute force. NASA uses an arraying technique, mechanically synchronizing multiple massive dish antennas like these at the Madrid Deep Space Communication Complex, so they act together as one giant, highly sensitive ear aimed into the night sky. To maintain this tenuous link, the data itself has to be compromised. Mission Control has severely throttled Voyager's transmission rate, dropping it from thousands of bits per second down to an agonizingly slow 160 bits per second, just to ensure the signal remains readable over the background noise of the cosmos. Eventually, an unavoidable physical deadline will arrive. By the year 2036, as Voyager moves further away, The Earth's angular position will appear to drift too close to the Sun from the probe's perspective. The sheer volume of solar radio noise will permanently drown out any single command we try to send. We can engineer around failing heaters and degrading thermocouples, but we cannot out-engineer the physical geometry of the solar system. No matter how efficiently we budget power, the expanding distance and the cosmic noise will snap the communication tether. Sometime in the early 2030s, the power from the RTGs will drop below the minimum voltage required to run a single scientific instrument. At that moment, the spacecraft will enter a permanent deep freeze. The transition from explorer to artifact will be mechanical and final. The digital tape recorders will halt. The structural materials will acclimate to the ambient temperature of the local interstellar medium. And the 32K memory computer systems will permanently freeze. The operational lifespan will be over. But the physical object remains. Because Voyager is bound to the Milky Way, it won't be carried away by the expansion of the broader universe. Instead, it falls into a silent, endless orbit around the center of the Milky Way galaxy, a path it will chart for billions of years. Its first cosmological milestone won't happen for 40,000 years, when it passes within 1.7 light-years of the star Gliese 445. Over the course of millions of years on this orbit, the probe's chassis will slowly sweep up drifting interstellar atoms. Eventually, this will accumulate into a thick, protective blanket of deep space ice over its titanium and aluminum hull. Tucked safely beneath that future ice is a piece of cargo designed explicitly for this exact phase of existence. The Golden Record, a gold-plated copper disc carrying the sounds, images, and biological data of human culture, will survive in the void for 1 billion years. These frozen relics will likely outlive the very species that built them. They will drift in the dark as the ultimate monuments to a civilization that learned to manipulate nuclear physics and massive radio arrays, simply to see how far into the dark they could reach.